In today's session, we'll discuss about some PYQs of synchronous machine. So again, synchronous machine is important topic, and every year you'll find some 2-3 questions from synchronous machine. So in today's session, we'll discuss about synchronous machine. I hope you'll enjoy this session, and I hope you'll learn something new from this session. Okay, so let's start this session, and let me tell you, I have selected some 10-11 questions from last year, starting from 2019 onwards, and 19, 18 and 17, like this. So I have selected some questions, so I'm trying to solve those questions, and I hope it will be a good revision for all of you. So let's start this session, guys. This is my introduction. I hope you are aware that I teach almost every subject, and right now I'm teaching with machines. So the next session will be on induction machine. This is synchronous machine session. In this session, okay, before starting this session, you better subscribe this channel and like this session if you have not liked it, or press the bell icon so that you get the notifications whenever the new session will be live. So there is one more, you can say, scholarship test is there. You can avail 90% scholarship on the preparation programs, whatever you want to join. So you will get 90% scholarship, and this will be on 24th of December, so better register, and the link is given in the description below, so don't forget to register. And let me tell you guys, this is the right time to join the test series, because the test series will help you to analyze your mistakes, your speed and accuracy. So better you join test series. Now Byju's Exam Prep is also giving you the test series, and it's affordable, so you can join this test series, and you'll get many tests, almost 60 plus tests will be there, and including the mock test, obviously. So you can check yourself. You can the interface is exactly same as the GATE exam interface, GATE exam, exactly it's same like that. Okay, so let's start the session, guys. Let's start solving the questions. The question number 1 is this. This question is from GATE 2014. 2 marks question is this. So in this question, the statement is, let me tell you the statement. Actually, my health is not well today, so I'm sorry for that, and there will be some, you can say, some interruption will be there because cough is there, so that's why. I hope you don't mind it. Anyway, so let's read this question. A 20-pole alternator having 180 identical stator slots. Okay, so there is an alternator. First thing is alternator, and it has 20 pole. So what you can do is you start writing this. Pole is 20, okay, and 180 slots, stator slot with 6 conductor in each slot. It means there are 180 identical slot. In each slot you have 6 conductor. So total conductor is 180 into 6. So total turns will be Z by 2. So it will be 90 into 6, 540. These are the total turns. Okay. So we found total number of turns. Now, if the coils are connected to realize single phase winding, the generated voltage is V1. If this alternator is a single phase alternator, then the generated voltage is V1. It is given. If the coils are reconnected to 3-phase star connected winding, okay, then the generated EMF voltage is V2. We need to calculate this ratio V1 upon V2. Now how to do that? It's very simple, guys. The method is very simple. First, all the turns are, you can say, are connected in a single phase manner. It means it's a single phase alternator. And in the second case, the turns are connected in star pattern, and it's working like 3-phase alternator. So now, if you know how to calculate this induced voltage, in the first case, the induced voltage is root 2 pi f n phase phi per pole into kW. Okay, this is the induced voltage in the first case, and the number of turns per phase is 540, because all the turns are single phase turns. So you can take this phi per pole. We need to calculate this kW, winding factor, and it is given that the coils are full pitched. Okay, assuming full pitched single layer winding. So the coils are full pitched. This means the pitch factor is 1, So I need to calculate the distribution factor so that I can get this Kw. Now, if the windings are connected in three phase, then the phase voltage is √2 pi f. N phase pi per pole into Kw. Now obviously this N phase will change. Number of turn per phase. Now these turns are distributed in three phase. So per phase the number of turns will be 1/3 of that. It means whatever number of turns you have used here, 1/3 of that turns will be used here whenever this alternator is connected in three phase manner. Okay. Similarly, the winding factor, this winding factor will also change. Flux per pole remains same. The flux per pole will not change. So better I write it N phase prime and Kw prime in case of three phase. Okay, so I told you what will be the change. If you connect the winding in single phase, then the number of turn per phase is 540. But if you connect the alternator in three phase manner, then the number of turns per phase will be 1/3 of 540. First thing is this. And the second thing is the winding factor will change. In the first case, the winding factor is, let's say, Kw. In the second case, the winding factor will be Kw prime. Now, if you take the ratio, obviously this will be cancelled. Pi per pole is cancelled. Why pi per pole is same? Because the field coils are same. In both the cases, we are taking the same field coils. Same pole, same field coils. Okay. So the field coils are same. That's why the flux per pole is decided by the field, let's say. So flux per pole will remain same. Now the ratio V1 upon V2 is N phase into Kw divided by N prime phase into Kw prime. Now let's try to calculate this ratio. V1 upon V2 is equal to, in the first case, what is N phase? When the alternator is connected in single phase, then the number of turn per phase is 540. So here you have 540, and in the denominator you have 540 upon 3. Okay, in the denominator you have 540 upon 3. Fine. In the first case, what is Kw? What is Kw? When the alternator is connected in single phase manner, then what is Kw? Now in single phase case, Kw, we know that Kw is Kp into Kd. Since the winding are full pitched, so Kp is 1, and Kd, what is Kd? So Kd we need to calculate. So Kd is sine of sigma by 2 divided by sigma by 2. This will be the Kd. Now how to calculate this? For single phase case, sigma is 180 degree. For single phase case, sigma is 180 degree, and for three phase case, phase spread, sigma is 60 degree. I think you must know this. If you know this, then it's easy to calculate the distribution factor. And Kp is 1 because windings are full pitched. So you can say that in the first case, or whenever the windings are connected in single phase case, then Kw is equal to 1 is Kp into sine 180 by 2, that is sine 90 is 1, divide by sigma by 2. Sigma is pi in single phase case, sigma is pi by 2. So this will be pi and divide by 2. So 2 will be in the numerator. I hope you understood it. Okay. This will be my Kw. Now in three phase case, again Kp is 1 and Kd. What is Kd? In three phase case, sigma is 60 degree. So if I put 60 here, so sine 30 is there. Sigma is 60, we know that. If sigma is 60, then sine 30, sine 60 by 2 is sine 30. Sine 30 is half. Divide by, here you need to put 30 degree in radian. In radian it's pi by 6. Is it fine, guys? Pi by 6. So the 6 I have written in the numerator. Is it fine, guys? Is it correct? So you can check that I have calculated the distribution factor. Okay. Now you can find this ratio. If you calculate this ratio, you can see that this 540 is cancelled. This 3 will come in the numerator, and wait a minute, this 3 is cancelled with this. Okay, because 6 upon 2 is 3, no? So 3 in the numerator and 3 in the denominator, it is cancelled. So this is 1 upon pi here. So if you take this 1 upon pi in the numerator, it will be multiplied with pi. So this pi is cancelled. So the ratio is 2 only. Okay, so answer is Delhi. So this ratio is 2. Okay, here windings are uniformly distributed. Yes, if nothing is provided to you, obviously we have to consider that the windings are uniformly distributed. That's why I have applied this concept, the sigma concept, because the sigma concept is valid if the windings are uniformly distributed. Now, how to know, why this method is applicable if the windings are uniformly distributed, and what is the, you can say, what is the property of distributed winding? In case of distributed winding, the angular slot pitch gamma, angular slot pitch gamma, angular slot pitch, that gamma should be less than 15 degree electrical. If gamma is less than 15 degree, then we usually assume that the windings are uniformly distributed. Now, how do I know that the windings are uniformly distributed? Look, there are 180 slots. In entire 360 mechanical angle, there are 180 slots. So per slot, the mechanical angle is 360 upon 180. Per slot, this is the mechanical angle. Now, what about the electrical angle? Electrical angle is P by 2 multiplied by P by 2. This is my angular slot pitch, gamma. This is my gamma. So if I cancel it, it will become 2 here, and this is cancelled with 2. So you can say gamma is 20 degree. Pole is, number of poles are 20. So you can say that angular slot pitch is gamma, which is comparable to 15 degree. Okay. It's a rough idea, you can say, because if gamma is less than 15 degree, then we call it uniformly distributed winding. But here in this case, gamma came out to be 20 degree. Angular slot pitch in electrical angle is 20 degree. Okay, so it's roughly approximate to 15 degree, and moreover, nothing is provided. Na? Slots per pole per phase, it is also not provided to us, or maybe you can calculate that slot per pole per phase. That way also you can solve. But I have solved using this sigma concept. This is comparable to 15 degree. That's why I have used the uniformly distributed winding case. Otherwise, what you can do is you can always apply this formula also. Sine of Q gamma by 2 divided by Q sine gamma by 2. For this, you need to calculate slot per pole per phase. Q is slot per pole per phase and gamma is angular slot phase. Gamma you have already calculated. Now you need to calculate Q value. How to calculate this Q value? This Q is slot per pole per phase. So in the first case, there are 180 slots and there are 20 poles and there is single phase. So in the first case, you have Q is equal to slots, which is 180, divided by per pole, which is 20, and there is only one phase. So in the first case, you have 9. Q is 9. In the second case, Q is 3. Okay. So this way also you can calculate the values. Okay. I mean, you can apply this formula also and you'll get the same answer approximately. So V1 upon V2 came out to be 2. I hope you understood it. But I have applied this sigma rule, okay, because I have assumed that the windings is uniformly distributed because this gamma is nearly equal to 15 degree. That's fine. Anyway, UG Sarma 180 by N. Okay, gamma is 180 by N. That's fine. What's the problem? Gamma is, look, there are 360, na? There are 360. 360 is the mechanical angle. In that mechanical angle, we have 180 slots. So per slot, what is the angle? Per slot, the angle is 360 upon 180. This is the mechanical angle. Okay. This is the mechanical angle and this came out to be 2 degree. Okay. Now I need to convert this 2 degree into electrical angle. That's why I have multiplied with P by 2. P by 2 is 20 by 2. Okay. So this 2 is cancelled. So you can say that gamma is 20 degree, number of pole. Okay. So 180 by N. 180 by N. What is N here? I don't know. I don't know which formula you are applying. Okay. But anyway, I hope you understood it, how to solve this question and how to approach this question. I hope you understood it and how to calculate this gamma. Many students apply a different formula for gamma. They directly remember the formula like if I write this formula, then they write 180. They write 180 upon number of slots per pole. Number of slots per pole. They remember this formula. I think this N is number of slot per pole, UG sigma. So you can apply this formula also. No? It's same like this. It's same like this. Okay. So I hope you understood how to calculate this question, how to solve this question. So it's very easy. Now let's proceed with the next question. Let's proceed with the next question. Okay, the next question is 1 mark question, and this question is asked in 2014. Okay, now the question is, in synchronous machine the hunting is predominantly damped by. Now tell me, the hunting is damped by. Shivam sir, please reply, confusion है इसमें formula में. Sir, if droop is defined no load to full load, sir rated क्या होगा? I don't know. F rated क्या होगा? If droop is defined from no load to full load. No, I'll maybe I can, if you can send me some question, then I can send you. And moreover, it's separate from the topic, because if the doubt is in from the question, then you can ask me. If you have different type of doubt, then better you ask me at the last of the class, or you can send me on the Telegram group. I'll reply you, don't worry. Okay. Anyway, look at the question. If the synchronous machine hunting is predominantly damped by. Now tell me, how to damp the hunting? Obviously, if you remember, there are damper windings. Now what these damper windings do? The damper windings will they have some kind of resistance, so the energy is whatever the energy is stored in the rotor due to hunting, that energy is absorbed by the resistance of the damper winding. So it means it is actually the ohmic loss in the rotor. So that's why, so you can say that to damp out the hunting, what we need to do is the copper loss in the rotor are necessary. These are the important thing. Copper losses in the rotor. Okay, I hope you understood, because you can understand that the damper windings are used to damp out the hunting. And the damper winding, what these damper winding do? The damper winding, they actually give the losses in the winding. Because of that losses, that the energy stored in the hunting, that energy is dissipated in the resistance of the damper winding. Okay, that's how the damping is. That's how the hunting is damped out. Okay, so I hope you understood it. Now let's come to the next question. This question is again 2014, 2 marks. Okay, this question, a non-salient pole synchronous generator. Non-salient means cylindrical. Okay, so we have a cylindrical synchronous generator having synchronous reactance of 0.8. Xs is given as 0.8 per unit. Okay, 0.8 per unit, supplying 1 per unit power to a unity power factor load. Okay, the power supplied is 1 per unit to a unity power factor. Power factor is 1. Okay, unity power factor load at the terminal voltage of 1.1 per unit. Vt is 1.1 per unit. Okay, so now I can make a diagram. So you can see that this is J 0.8 per unit. Here the voltage is 1.1 per unit. Okay, voltage is 1.1 per unit. This is 1.1 per unit. Now here the load is connected, and the load, the power is 1 per unit. Okay, the load is taking 1 per unit power. Okay, or you can say that the 1 per unit power is supplied to the load. Neglect the armature resistance. The angle of the voltage behind the synchronous reactance with respect to the angle of the terminal voltage in the degrees. Okay, so he is asking about this angle, this delta angle. Excuse me. So this is EF angle delta. We need to calculate the angle difference between this voltage and this EF. Let's assume that this voltage angle is 0 degree. I have assumed that this terminal voltage angle is 0 degree. Now I need to calculate the angle delta. Okay, that difference is asked. If you can understand the question, then this difference is asked. We need to calculate this difference. Now how to calculate? This is again a question of network theory. Okay. Excuse me guys, actually my health is not with me, that's why. Okay, so now what I can do is, this question, I have converted this question into network theory. This is your, this is the right approach. Whenever you see the questions from electrical machine, try to convert that question into a network theory problem. Okay, so I have converted this machine question into network theory question. What I need to do is, I need to calculate this voltage along with the angle. Now how to calculate that? We know this voltage. If somehow we can calculate this current, if somehow we can calculate this armature current IA, or you can say the load current, if somehow we can calculate this current, then you can say that we can calculate this EF and the angle delta. Okay, so it's simple. Now how to calculate this current? It's very simple. We know that the power factor is unity. It means whatever this current is, the angle of this current will be same as the angle of this terminal voltage. That's why the load will be unity power factor. Na? The load will be resistive. It means the angle of this current is 0 degree, but we are not sure about the magnitude of this current. Okay, so let's try to calculate the magnitude of this current IA, but the angle is 0, that's for sure. Now how to calculate the magnitude? It's very simple. We know that the power is 1 per unit. So if you calculate the power here, so power is voltage, which is 1.1, into current, which is which is IA, into cos of angle between them. Cos of angle is 1, is equal to 1 per unit. You know that. So from here, IA will be equal to 1 upon 1.1. So we have calculated the current value, IA value, and the angle is 0 degree itself. Okay. Now we have calculated the current value, and we know that the angle is 0 degree. Now how to calculate this EF? It's very easy. You can apply this KVL. Na? So at this point the voltage is 1.1 at an angle of 0 degree plus this voltage, and this voltage is J 0.8 into this current, and this current is 1 over 1.1 angle 0 degree. This will be EF angle delta. Is it fine, guys? We need to calculate the angle itself. Okay, other things, the magnitude of EF is not necessary. We need to calculate this angle delta. So now you can calculate this angle delta. You just need to solve this, and we need to calculate the angle of this quantity that will represent the delta. Now if you have the calculator, please calculate this delta and tell me. Let me tell you what answer I got, because I have already solved this question. So let me check what answer I have got from this question. Yes, this angle came out to be, I think, 33.49. Is it correct, guys? 33.49. This is 33.49, and the magnitude is 1.319, 1.32, you can say 1.32, 1.32, and angle is 33.49. Is it correct? Please check it. Please check whether this is correct or not. Okay, so now we calculated this EF and this angle delta, and we need to calculate the difference in the angle of this voltage and this voltage. So the difference is delta itself, and delta came out to be 33.49, 33.49 degrees, because in degrees it is asked, na? So the answer is 33.49. Is it correct, guys? Please tell me. I think the calculation is fine. I think I have done the calculation correctly. So this is the correct answer. It's a network theory problem. So the good thing is, and this is the right approach. The approach should be, you have to convert the machine problem into network theory problem. Okay, remember this point. In the previous question also, if you look at this is the direct formula based question. Otherwise you must have converted into again network theory. You have to convert the question into network theory problem. You just draw the diagram, na? If somehow you can draw the circuit diagram, or somehow you can draw the phasor diagram, then it will be easy to understand, then it will be easy to calculate. Okay, so whenever you see the machine problem, try to convert this into network theory problem. I think it will be easier then. Okay, let's come to the next question. Consider the statement consisting of a synchronous generator. Okay, so there is a synchronous generator working at a lagging power factor. Synchronous generator is working at a lagging power factor. What does it mean? First of all, let me check the statement. This is again, let me check the yeah, it's 2016 1 mark question. This is 2016 1 mark question. So in this question, consider a statement consisting of synchronous generator working at a lagging power factor. So synchronous generator is at lagging power factor. What does it mean? It means can we use E cos delta equal to V? In the previous question, okay, you want to apply this formula, na? EF Vt upon XS sin delta. is equal to the power, active power 1 per unit. Now EF, the magnitude of EF is unknown, magnitude of VT is known, which is 1.1, and XS is also known, 0.8. So you can say EF sine delta, you can calculate this value. Okay, you can calculate EF sine delta here, but again delta is unknown, so that's why GATE aspirants. So I hope you get the idea. From here I can't solve. The problem is we have two unknown, EF sine delta, EF sine delta. You'll get EF sine delta from here, that is XS upon VT. XS is known, VT is known, so you can calculate this value. Now the problem is you can't proceed from this. Okay, so this is the main reason. Okay, moreover there is one more way, na? You can plot the phasor, and then also you can solve this question. If you can plot the phasor, let me draw the phasor diagram. If somehow you can draw the phasor, then this will be my VT. Let's say VT is at 0 degree, and the current IA is in same phase. So VT plus JIXS is EF. In alternator, VT plus JIXS, this is JIXS and this is EF, okay, and this is delta. So you can see that EF sine delta is this length, EF sine delta is IXS, okay, EF sine delta is IXS, EF cos delta is VT, EF cos delta is VT, EF cos delta is VT, okay, you can say like that. EF cos delta is this length VT, okay, and EF sine delta is IAXS, so this must be equal to IAXS. Is it fine, guys? IAXS. So from here you can check IAXS, okay. So EF sine delta is IAXS and EF cos delta equal to VT. From there also you can calculate the value of delta. I think it's easy peasy, okay. Vishwanathan Murli, sir, Q is 0, EF cos delta is V, na? Two questions, sir. For unity power factor, EF cos delta is VT. No. GATE aspirant, don't remember. You don't. One relation is this. One relation is this power relation, active power relation. Okay. So the active power relation is this is 1 per unit power which is delivering to the load. Okay. So you can write EF VT by XS sine delta equal to 1. Okay, so from here you will get this equation, okay, and one relation you can get from the phasor diagram. If you can draw the phasor diagram, this is my terminal voltage VT and the current is at unity power factor, so IA will be in the same phase with VT, and then VT plus JIXS is equal to EF, okay. So this is the phasor diagram. Now using the phasor diagram we can say that EF cos delta is VT and EF sine delta is IXS, or EF sine delta is this. Now from these two relations you can calculate delta. I think it's easy peasy now, okay. I think now it's easy. You can divide and you'll get 10 delta, and using 10 delta you can calculate the delta value, okay. So directly you will get the delta here. I mean there are multiple ways. I have calculated this using the KVL. You can use the phasor approach, no problem. Both are simple, both are easy, okay. Now let's proceed with the next question. Look at the next question. Consider a system consisting of synchronous generator working at a lagging power factor. So we have a synchronous generator which works at lagging power factor. Now tell me, when the synchronous generator is working at lagging power factor? Obviously when the load is inductive. If the load is inductive, then the inductive current is demanded by the load, and you can say that the generator is supplying the lagging reactive power. Is it fine? Generator is supplying the lagging reactive power. If the load is inductive, if the load on the generator is inductive, that it means the generator is working at lagging power factor. Remember, the power factor is decided by the load itself, okay. So you can say if the generator is working at lagging power factor, it means the lagging reactive power is coming out from the generator. Now tell me, when does the lagging reactive power will come out from the generator? Obviously if the generator has high amount of field inside it. If high amount of field inside it, then it will try to supply that field outside the generator, because that high amount of field is not required for the generator to maintain the terminal voltage VT equal to 1 per unit, let's say. Now if you increase the excitation inside this generator, then it will try to give the reactive power at the terminals. Okay, it will try to give the reactive power, lagging reactive power to the load. It means you can say that the lagging reactive power is coming out from the generator. Is it fine, guys? So it delivers lagging reactive power. I hope you understood it. What is the meaning of this working at lagging reactive power, lagging power factor? So if the old generator is working at lagging power factor, it means it is delivering the lagging reactive power. Okay, and there is a synchronous motor working at overexcited condition. Now again, there is a motor which is at overexcited. Overexcitation means, again, the field excitation is higher, which is required. Whatever the requirement of the field excitation is, it is higher than that. Okay, if the field excitation is higher, let's say if it is overexcited, then what will happen is, again, the motor will also try to give back the lagging reactive power. It will try to send the reactive power to the supply system. It means the motor will act as a load. No, motor is acting as a load, because motor is a type of a load, because motor always demand power. That's why we take motor as a load. So if the motor is overexcited, it means the load is overexcited, and the load is transferring the lagging reactive power to the source, because it is overexcited. Overexcitation means the lagging reactive power is actually transferred from the load to the source. It means the motor is working at leading power factor. Okay, the motor is working at the leading power factor. So what he is saying, we have a generator which is working on lagging power factor, and synchronous motor which is overexcited condition, and a directly grid connected induction generator. There is an induction generator. So remember, old generator is also supplying the lagging reactive power, and motor is also supplying the lagging reactive power. Both are supplying the lagging reactive power. And a directly grid connected induction generator is there. Consider a capacitive VAR to be source. Okay, he's saying that we have to assume that the capacitive VAR, it means leading reactive power, to be a source, and inductive VAR to be the sink of reactive power. Okay, inductive VAR to be the sink of reactive power. Which one of the following statement is true? Which statement is true? Now, the first statement is synchronous motor and synchronous generator are sources. Yes, that's correct. Synchronous motor and synchronous generator are sources, because they are supplying lagging reactive power. They are supplying lagging reactive power, and it is given that consider the capacitive VAR to be the source and inductive VAR to be the sink. It means if something is taking inductive reactive power, if something is taking lagging reactive power, we call it sink. And if something is giving leading reactive power, if something is taking leading reactive power, not giving, what is the meaning of this statement? Let me tell you. Let's say I have a load. I have this load. If this load is taking lagging reactive power, we call it sink. Okay, and if it takes leading reactive power, okay, if we take leading reactive power, we call it source. It is given that in the question. We call it source. Now, leading reactive power, if it is taking leading reactive power, it means it is giving lagging reactive power back. Something which is taking leading reactive power, it means it is giving lagging reactive power. So something which is providing lagging reactive power will act as a source, and something which is demanding the lagging reactive power will act as a sink. You can say like that. Now we know that the motor is again working overexcited, so it is supplying the lagging reactive power. The generator is also supplying the lagging reactive power. So if something which is supplying the lagging reactive power, it means actually they are taking leading reactive power. Actually they are taking capacitive reactive power. Okay, so you can say that they will work as a source. They will work as a source. I hope you understood it. Okay, so you can say that from this statement, you can say that since motor and generator both are supplying the lagging reactive power, it means they are taking leading reactive power. Alternatively, you can say that supplying lagging reactive power means taking leading reactive power. So both are taking leading reactive power. If both are taking leading reactive power, they will work as a source. And the induction generator is taking lagging power. Induction generator is taking lagging power. And generator and motor, that synchronous generator and synchronous motor, they are supplying lagging reactive power, so they will act as a source and the induction generator will act as a sink. Okay, so I think A is correct. No need to look the further options. Okay, so answer A is correct. It's easy. Induction generator is as a sink of reactive power. I think you have understood it. Okay, so this question is again very easy. I hope you can understand this. Okay, let's move to the next question. So the next question is a 3-phase 50 hertz. I don't need to read those other options because this is not MSQ. Okay, a 3-phase 50 hertz salient pole synchronous motor. Okay, so we have a synchronous motor. First of all, remember this point. So we have a synchronous motor. Has a per phase direct axis reactance XD. XD is provided as 0.8. Okay, and per phase quadrature XQ. XQ is given as 0.6 per unit. Okay, that's fine. The resistance of the machine is negligible. Okay, that's fine. It is drawing full load current at 0.8 power factor leading. Okay, so a power factor is 0.8 leading. And remember, this is synchronous motor. Remember this point. It's not generator, it's motor. And this is cylindrical synchronous motor. Power factor is given as 0.8 leading. When the terminal voltage is 1 per unit, he's saying that when Vt is equal to 1 per unit, when the terminal voltage is 1 per unit, per phase induced EMF, I need to calculate EF. What is the EF? We need to calculate that. So how to calculate this question? Again, you can use the phasor diagram method. You can plot the phasor diagram and you can solve accordingly. Let me draw the phasor diagram first. In synchronous motor, remember, in synchronous motor, Vt is ahead of EF. And in synchronous alternator, EF is ahead of Vt. Like in this question, since it was synchronous alternator or synchronous generator, that's why EF is ahead of Vt, anti-clockwise. EF is leading Vt. But in motor, Vt actually leads EF. So let's say on this side, I represent EF. Let's say on this side, I represent EF. This is my EF. Okay, so Vt should lead. Vt should be here. Vt should lead. By delta angle, Vt should lead. And since IA is leading, that's why IA should be on this direction. This angle is theta. This theta is the leading angle. Okay, theta is this leading angle. Now, if you break this IA, you can break this IA in two components. There is one component in the phase of EF and there is one component at 90 degree to EF. Okay, we call it IQ and we call it ID, if you remember. Is it fine, guys? I think this is correct. Tell me, everyone, is it correct? We call it IQ and this is ID. Now, if you draw the phasor diagram, EF, this is my EF. Remember, in motor, the current supplies from the terminal voltage Vt to EF. Vt to EF. So, in motor, if you start from EF, from backside, if you start from the backside, then EF plus J IQ XQ plus J ID XD will be Vt. So, in case of motor, EF plus J ID XD plus J IQ XQ is equal to Vt. If you remember the KVL equation. In case of motor, if you remember the KVL equation, this is the KVL equation. In alternator, remember, alternator, we look at the terminal voltage, okay, and we try to add the drops in the terminal voltage to get the EF. Okay, let me tell you about this cylindrical rotor alternator. In cylindrical rotor, this is the diagram, na? This is the diagram. Okay, this is my Vt, this is my EF. So let me tell you guys, this is my IA. So this is the drop, IXS. So whenever you write for the synchronous alternator, then you have to add this Vt plus this drop, you will get EF. It means EF is greater than Vt, you can say that. or maybe EF will be sum of Vt plus JIXS. But in case of motor, motor actually the current is reversed. In case of motor, the current is reversed. In case of motor, the current is reversed. The current is in this direction. So the polarity of drop will be like this. Okay, JIXS will be of this direction. So you can say that if I write the KVL in this direction, then EF plus JIXS you will get Vt. It means in case of motor, you start from EF to Vt side, and in case of alternator, Vt to EF side. Okay, so remember this way you can do like this. So that's why in case of salient pole, again you can assume the same thing. So in case of salient pole, since it is a motor, so in case of motor you start with the from the EF side. So EF plus JIDXD plus JIXS is Vt. You know that. Now if I can draw the phasor diagram, then this is EF, this is IQ, this is ID. So EF plus JIQXQ. JIQXQ will be on this side because IQ is on this side. So JIQXQ is on this side. JIQXQ plus JIDXT. If ID is on this side, then JID will be on downward side. Okay, JIDXT. And this will be my Vt. Is it fine, guys? And this angle we call delta. This angle we call delta. Okay, and this angle IA and EF, this angle I call psi. Psi is called internal power factor, that is delta plus theta. Is it fine, guys? So that is delta plus theta. So this is my, you can say, this is my phasor diagram. Now using the phasor diagram, I can calculate EF. I can calculate the EF. How to calculate EF? Excuse me. Now how to calculate the value of EF? Tell me, guys, what should be the method? What should be the right method to calculate this EF? We know this ID, we know this IQ, we know the power factor, we know this theta. This theta is known to us. Okay, we know theta, and we know Vt. Obviously Vt is also known, but ID and IQ are not known. ID and IQ are unknown. So now if you don't know ID and IQ, then how to calculate this EF? Because everything is known, only ID and IQ are unknown. So first thing is to calculate ID and IQ. If somehow you can calculate ID and IQ, you can calculate this EF. Or there is one more method, and that method is, do you know IA? Do you know IA? What is IA? Okay, let me check. It is drawing full load current. It means IA is 1 per unit. You know this IA. IA is 1 per unit. Full load current. Full load current means 1 per unit current is there. Okay, so we know IA as 1 per unit. IA is known to us. If IA is known to us, then I can calculate IQ and ID. I can calculate these two currents. How to calculate these two currents? We need to calculate this internal power factor angle psi. Now how to calculate this internal power factor psi? How to calculate this internal power factor psi? Look, if you remember, if you use the phasor diagram, from the phasor diagram I can say that tan psi is equal to, if you somehow can calculate tan psi, this angle is psi, so let's extrapolate this IA. I have extrapolated this IA, okay, and tan psi is perpendicular over base. Okay, so what I did is I extrapolated here, and also I have plotted this, wait a minute, this is my Vt, this is theta. So what you can do is, you can take a perpendicular here, so this length will be Vt sin theta, this length is Vt sin theta. So we need to calculate this tan psi. If you can remember the formula for tan psi, in case of motor, then you can apply that directly. You can find this psi. Once you get this psi, you will get this ID and IQ, and you can put the value of ID and IQ and you can calculate the EF. It's simple. But the challenge is, But the challenge is we need to calculate this psi angle. Okay, now how to calculate this? Tell me guys. Viswanathan Murli, P psi is 0. Which psi you are saying? Okay, you are saying this psi is 0. No sir, it will not be 0. Okay, power, you are saying power is again not 0. Okay, so how to calculate this 10 psi? If you can remember the formula, you can directly apply that. In leading power factor and in case of motor, 10 psi will be equal to, let me tell you, 10 psi will be equal to Vt sine theta, I don't know whether it is correct or not, plus Ia xq, I don't want to prove this, okay, upon Vt cos theta plus IRA. Since RA is 0, so we will not write this. Okay, I think this is the correct answer. For leading power factor, in case of synchronous motor, 10 psi is this. Okay, please check it. Please check this formula whether it is correct or not. Let me check. I think this is correct. It should be minus here. Okay, in case of motor, I think it should be minus here. So it is minus actually. Should be minus here. Okay, so this is the formula for 10 psi. Now, how to remember this formula? It's a challenging formula. How to remember it? Better you remember it. Otherwise, it will be difficult to calculate this 10 psi from this phasor diagram, because you have to do many type of manipulations and then only you will get this 10 psi. Okay, so better you remember this formula. Now, how to remember it? How to prove it? Obviously, you have to plot the phasor diagram completely and then only you'll prove it. I'm not going to do that because right now it's not a, you can say, not a theory class, but let me tell you how to remember it. There are methods. And what are those methods? Actually, there are two cases for alternator motor and lagging power factor, leading power factor. So actually there are 4 cases. So let me tell you what are those 4 cases and how to remember this formula 10 psi, because otherwise it's difficult to prove it. It's not that much difficult. Obviously you can use the phasor diagram and you can prove it by just doing some manipulation, but let me tell you how to remember it. Okay, so first cases, there are cases like motor and alternator. Okay, and first let's do it for lagging power factor. Lagging. For lagging power factor, this 10 psi is equal to for motor. First of all, I'm looking for motor, or you can say you can write for alternator first. So for alternator, this formula should be Vt sine theta plus Ia xq divided by Vt sine theta plus Ia xq divided by Vt cos theta plus IRA. This is the formula, guys. This is the formula for alternator 10 psi for lagging power factor. Remember this. For lagging power factor for alternator, this is the formula. Now you need to remember this. Okay, now let's come for the motor. In case of motor, we know that the Ia direction is opposite. So what you can do is you can replace this Ia with minus Ia, nothing else. Okay, in case of motor, you can replace this Ia with minus Ia and you will get the 10 psi. So it will be Vt sine theta minus Ia xq divided by Vt cos theta minus Ixq minus IRA. Okay, so this is the formula, guys. You just remember like this. This is a simple method to remember. Okay, Ixq. Okay, this 10 psi is for alternator, this is like this, and for motor you just change this Ia with minus Ia. Okay, change Ia with minus Ia. Okay, so for motor you can write like this. I hope you understood it. Is it fine, guys? Is it fine? So remember this 10 psi is like, you can write like this. Now for leading power factor, how to write for leading power factor? Now for leading power factor, this is for lagging. Now for leading power factor, Now in case of leading power factor, we use this formula again. Tan psi is equal to, we again using the same formula, but since the power factor is leading, then this theta can be replaced with minus theta. Okay, this theta can be replaced with minus theta. In this expression, we can replace this theta with minus theta if the power factor is leading. Okay, so this tan psi for alternator, it will become, this theta can be replaced with minus theta, so it will be Vt sin theta with negative sign plus Ia xq divided by Vt cos theta plus IRA. But let me tell you guys, this quantity is negative. This quantity came out to be negative, but this psi cannot be negative. So what you can do is you take minus common here. So it's just a method to remember. It's just a method to remember. So if you take minus common from here, so it will be positive and it will be negative. Okay. So this way you can remember the tan psi. In case of leading power factor and in case of alternator, tan psi is this: Vt sin theta minus Ia xq divided by Vt cos theta plus IRA. Okay. So you can remember like this. I hope you understood it. Let me check this formula again. I think this is correct. Now for motor. For motor, what is this tan psi? I told you for motor you just change this Ia with minus Ia. So if you are going to change this Ia with minus Ia, then what will happen? Here you will get plus sign and here you will get minus sign. Okay, so you will get Vt sin theta plus Ia xq divided by Vt cos theta plus minus IRA. Okay. So this is the way to remember it, minus IRA. Okay. So this tan psi, you can remember like this. Only you need to remember this. For lagging power factor, for alternator, you remember this. No? Then for motor or maybe for leading power factor, you can easily calculate. Okay. So you can remember this, this formula like this. I hope you understood it. How to remember these formulas. Tan psi, how to calculate this tan psi. Once you get this tan psi, now in case of motor, if you can see that in case of motor, this is my tan psi. This is the formula for tan psi, and Ra is negligible. That's why I have neglected it. From there, I can calculate this psi. Once you get this psi, then you'll get this IQ and ID. You can put the IQ and ID here and you can calculate this EF. I think it's easy peasy now. Is it fine, guys? Lag or lead impacts the direction of X, so change the sign of X terms. Is it correct, sir? Okay. Actually, the lag or lead, if you lag it or lead it, then this theta will change, no? Because if the angle is, let's say, leading, this theta is on this side. If Ia is lagging, this theta will be on this side of Vt. That's why if I am changing lagging to leading, then what I'm changing is theta only. I'm changing theta only. Okay. So that's the correct way to write. I mean, there is a method to remember. You can remember like changing this X. You can do the same thing again. You can do the things like this, that you can change the sign of this X. Okay, that's also correct. But I don't do like this. I think that this theta is changing. Theta is changed to positive to negative. For lagging, let's say theta is positive. Now for leading, you just change the theta. If you change the theta, it will be negative, it will be positive. But if it is negative and it is positive, then you will get psi to be negative. We want it positive. So remove this minus sign. Take this minus sign common and you will get this. Okay. So this way you can write for tan psi. Okay. This is the right method to remember it. But anyway, there can be some different method also. So you have to remember this formula. Okay. So I hope you understood it. So using the formula, you can calculate this tan psi. So first of all, let's calculate this tan psi. So this psi came out to be, I have calculated this psi. So let me check the psi value. The psi came out to be 56.30. You can check. You can put the value of Vt. Vt is provided to us. Theta, cos theta is this. So sin theta is 0.6. Okay. And Ia is 1 per unit. Xq is also provided. So divide by Vt cos theta. So this way you can get psi is equal to 56.30. Is it fine, guys? This is my psi 56.30. Please check it. I think this is correct. Please check this, guys. My answer, my psi is 56.30. Murli, you are getting different answer. Okay, 56.30. This is the psi value. Now, if you get the psi equal to 56.30, then you can calculate IQ and ID. Now, IQ will be equal to. What is IQ? Tell me, guys. IQ is equal to IA cos psi. IA is 1 per unit cos psi. Similarly, you can calculate ID is equal to IA sin psi. You can calculate IA and IQ, ID and IQ. Okay, you can calculate ID and IQ. Once you get this ID and IQ, you can put it here and you can calculate EF. So if you put it here and you calculate EF, then the EF value is, let me check what is EF. So EF came out to be 1.606. Okay, 1.606. This is my EF. Please check it. Please check it whether I have done it correctly or not. So what I did is I converted the machine problem into network theory problem, the KVL equation. Okay, I have converted this machine problem into network theory problem. So for converting the network theory problem, I need ID and IQ. Now how? There was a glitch. Wait, can you watch me? Can you see me? Tell me, guys. I think there is a glitch. So let me. Wait a minute. I think there is a problem. Wait. Okay, wait a minute, guys. I think there is a problem with the video. Let me see. Here it is fine. Okay, so there was a glitch actually. Oh, give me 1 minute. Okay, tell me, is it fine now? Is it fine now? Tell me, guys. Is it fine now? Tell me. I think it's perfect now. Okay, so I told you that I have converted this problem, that machine problem, into network theory problem. I have written this KVL equation, and then to calculate EF from this KVL equation, I need to calculate this ID and IQ. For ID and IQ, if you draw the phasor diagram, I need psi angle. So I have written this 10 psi. Okay, this 10 psi. I have written this 10 psi and calculated this psi angle, and then I use this psi angle to calculate this IQ and ID. Is it fine, guys? So I think this is easy peasy, and this way you can solve the problem. So EF came out to be 1.606. I hope this is correct. So this is the I mean, you can say this is the way that I have solved it, or there is one more way to calculate this EF. We know that using the phasor, this is VT. We know that this is VT. So what you can do is you take this projection. This will be VT cos delta. So VT cos delta plus this length is IDXD. VT cos delta plus IDXD. Now you need to calculate this delta, and this delta is, we know that psi is delta plus theta. Theta is already known to us. Cos theta is 0.8. So theta is 36.86, whatever. Okay. So psi minus theta, you will get delta. Once you get delta, you will get VT cos delta plus this IDXD. You know this ID. So IDXD, you just add it. VT cos delta plus IDXD, you will get EF. Okay. So there is one more point. I hope this is correct. In question 4, motor leading kVAR. Okay, Pawan, you are asking about question 4. Yes, in question 4, motor is overexcited. It means motor is delivering lagging reactive power. Because it is overexcited, it has higher value of flux inside it. If it is overexcited, it has higher value of flux inside it, then it will start delivering the lagging reactive power. It means it is taking leading reactive power. It is taking leading reactive power, or you can say it is start delivering lagging reactive power. If it takes leading reactive power, it will act like a source. Leading reactive power, if something is taking leading reactive power, we call it source. So motor is again act like a source. I hope you understood it. Now let's come to the next question. Question number 6. What this question says, the power consumption of an industry is 500 kVA. The power consumption is given as 500 kVA, okay? At 0.8 power factor lagging, okay? A synchronous motor is added to raise the power factor of industry to unity, okay? So it's a power factor improvement question. Again, it's a network theory question, okay? So in the first case, the apparent power is 500 kVA and the power factor is 0.8. Now tell me about the active power. So the active power demand of the industry is 500 into 0.8, that is 400 kilowatt, and the reactive power is 500 sine is 0.6. So 500 into 0.6 is 300 kVAR and lagging, okay, because the power factor is lagging. So this is the demand of the industry, this much of active and this much of reactive. Now what we have done is we have connected a synchronous motor to raise the power factor of the industry to unity. It means the synchronous motor itself is providing that lagging reactive power, then only the power factor will become unity, na? If the power intake of the motor is 10 kilowatt, 100 kilowatt, then the power factor of the motor. Now what this motor does is we have connected a motor. This motor, and we have the industry. Here we have the industry. Okay, let's say this is the supply we have, and the motor is connected in parallel with it. Okay, the motor is connected in parallel with it. So this motor, what this motor does, this motor takes 100 kilowatt. This motor takes 100 kilowatt active power, and it supplies 300 kVAR to this industry. To this industry, it applies 300 kVAR so that the industry will work at unity power factor. Okay, because then the reactive power demand of the industry from the source side is 0. Only active power is demanded by the industry. That's why you can say that the power factor is unity. So now the motor is supplying this reactive power, and the motor also takes active power. So you can say the motor is delivering this much of lagging reactive power. If the motor is delivering lagging reactive power, it means you can also say that it is actually taking leading reactive power. If lagging is given, alternatively you can say that if lagging is given, it means leading is taken. Okay, so motor is taking this much of leading reactive power and this much of active power. It means motor is working at leading power factor. Okay, now what is the power factor now? So power factor is active power divided by the apparent power. And what is the apparent power? Apparent power is 100 square plus 300 square. Okay, this is the apparent power, and this is the leading power factor. I hope you understood it. This is the leading power factor on which the motor is working. Is it fine, guys? So the answer came out to be 0.316. Okay, 0.316, whatever, you just calculate this numerical value. Okay, I hope you understood it. Is it fine, guys? Is it fine? So now this was easy. Let's move to the next question, question number 7. Now in question number 7, you can see that a three-phase 50 hertz star connected cylindrical rotor synchronous machine. So we have three-phase 50 hertz, okay, star connected synchronous rotor, cylindrical rotor synchronous machine. So we are not sure about alternator or motor, because machine can be motor or it can be alternator. Okay, is running as a motor. Okay, now he is saying that it's a motor. Okay, so there is a three-phase 50 hertz star connected cylindrical rotor motor. The machine is operated from a 6.6 kV grid. Okay, so you can say that the terminal voltage is 6.6, the line voltage is 6.6 kV, and draws a current at unity power factor. Okay, and the power factor is unity. Power factor is unity. The synchronous reactance of the motor is, okay, Xs is given as 30 ohm. Synchronous reactance is 30 ohm per phase and the load angle delta is 30 degree. Okay, perfect. The power delivered to the motor in kilowatt. What is the power delivered to the load? What is the power delivered to the motor? Okay, in kilowatt. I need to calculate the active power. We know that the active power is E of Vt by XS sine delta. This is the active power. We know that. It's very simple. Now, how to calculate this EF? Vt is known to us. Vt is known to us. Now, XS is also known to us. Delta is known. EF is unknown. Now, how to calculate this EF? Once you get this EF, then easily you can calculate the active power delivered to the motor. Now, tell me guys, how to calculate this EF? How to calculate this EF? Okay. Power factor is given to us. Power factor is unity. Now, if I draw the phasor diagram, this is my Vt. Remember, this is a motor. This is the motor. So better you write this EF. This is EF, and you know that in case of motor, Vt should be ahead of, or rather you can make it Vt. Na? You can make it Vt. This is my Vt, terminal voltage, and motor takes this current Ia. Now, in case of motor, we know that if you write the KVL equation, then Vt minus JIXS is EF, because this is the diagram. Na? This is the diagram of a cylindrical rotor motor. This is the diagram, guys. Current is coming like this, Ia. This is my Vt. So you can say that Vt minus this JIXS is equal to EF. Now tell me, if Ia is in this direction, JIXS will be in this direction. JIXS will be in this direction, and minus JIXS will be in this direction. So we call it minus JIXS. This is minus JIXS. And this will be my EF. Okay. This will be EF. Is it fine, guys? And this is delta. Now what I need to do is, I need to calculate this EF value. How to calculate this EF value? It's very simple. We know that EF cos delta. From this phasor diagram, I can say that EF cos delta is Vt. If somehow we can calculate this Vt and this delta, then we can calculate this EF. So EF is easy. Now EF came out to be Vt upon cos delta. Vt upon cos delta. It's very simple. Okay. Vt upon cos delta. You put this EF value here. So if you put the EF here, then the active power per phase active power is EF. EF is Vt upon cos delta. So it will become Vt square upon XS. Sine delta upon cos delta is 10 delta. Is it fine, guys? This is my active power. This is my active power per phase, because I am writing this per phase voltage. You have to multiply it with 3. Then you will get 3 phase active power. Now how to calculate this value? 3 into, what is the per phase terminal voltage? Per phase terminal voltage is 6.6 upon root 3. This is the per phase terminal voltage. Because 6.6 kV is the line voltage, and the per phase voltage is divided by root 3. You will get the per phase voltage. Okay. So 3 times of 6.6 into 10 raised to power 3 divided by root 3 square. Okay. Divide by XS. What is XS? XS is 30 into 10 delta. Now delta. What is delta? Delta is 30 degree again. Is it correct, guys? So this is the active power. Now you can see that this 3 is cancelled with this. Okay. And this will be 6.6 into 6.6. Okay. 6.6 square. Na? 6.6 into 6.6. Divide by 30. 10 30 and into 10 raised to power 6 is there. So megawatt. You can say that this will be in megawatt. Is it fine? 10 raised to power 6 is there. Na? So we call it in megawatt. So you can calculate this value, but the answer should be in kilowatt. So multiply with 1000 and you can replace this in kilowatt. Okay. You can calculate this power like this. So the answer came out to be, if you can calculate this answer came out to be 838.3. 838.3 kilowatt. Is it correct, guys? Have you understood it? Tell me. It should be 838. Please check your answer. Please check your answer. Okay. It should be 838. I think it should be 838. Please check it. Is it fine, guys? Tell me. Is it fine? Please check it. Let me check. I think it's 8:38. Please check it, guys. Please check your calculation. Okay. Perfect. Gate aspirant. Per unit voltage of two synchronous machine through a lossless line are this angle 10 degree, one angle 0. What will the real reactive of machine 1 in terms of positive or negative? How to do it, sir? Per unit voltage of two synchronous machine through a lossless line are this angle 0. It means you are saying, I mean, because your question is not correct now, because you are not saying that in which manner these two synchronous machines are connected. According to your question, I can assume that at one end you have one machine, at the other end you have some other machine. Let's say at one end one machine is connected and the angle is and the magnitude is 0.95 angle 10 degree. Okay, so you are saying that we have a lossless line. This is a lossless line, and here you have machine 1. Okay, and the machine 1 angle is 0.95 angle 10 degree, and here you have machine 2, and the magnitude is 1 at an angle of 0, 1 at an angle of 0. Now you want to calculate how much active power and reactive power is supplied from this side. So it's very simple. Okay, what is the real active and reactive power in case in terms of positive or negative? How to do it, sir? Okay, let me tell you. First you need to calculate the reactance of this line, because the line is lossless. You need to calculate the reactance of this line. What is the reactance of this line? It should be provided, otherwise you can't do it. Okay, because this will act as a VT, this will act as a EF. Okay, this is EF, this is VT. You need to calculate this X, then only you can calculate active power and reactive power. Okay, if this question is there in, I mean, this cannot be a standard question, because it might be possible that this question is given in some basic books like Indian author book. Okay, because they do the copy. Okay, they copied from somewhere else. Okay, or it might be possible that this question may be asked in some JEE exam, because they don't think much about it. Okay, but this is wrong actually, because you need to provide this axis. What is the reactance of this line? Okay, otherwise you can't calculate the active and the reactive power. Okay, so anyway, I hope you understood it. So this answer came out to be 838.3. Okay, that's fine. Now let's proceed with the next question. In the next question, what is given is two parallel connected 3-phase 50 Hz 11 kV star connected synchronous machine A and B are operating as synchronous condensers. Okay, so there are two parallel connected 3-phase 50 Hz 11 kV star connected synchronous machines A and B operating as synchronous condenser. They together supply 50 MVAR at 11 kV grid. Okay, so there is an 11 kV grid and two machines are connected in parallel. This is machine 1 M1 and this is machine 2 M2. Okay, and both are providing the reactive power. Okay, both are providing the reactive power. The total reactive power supplied by them is 50 MVAR. Current supplied by both the machines are equal. If they are supplying equal currents, then the terminal voltage is same for both of them. So you can say that both are supplying same reactive power, simply because the voltage is same for both of them, the terminal voltage is same for both of them, and the current are also equal. So you can say that both are providing same reactive power, because current is same, voltage is same, and obviously they are providing reactive power. It means the power factor is 0. Because they are providing only the reactive power. So both of these motors, the power factor is 0. So if power factor is 0, then you can say that both are providing reactive power. So 25 MVAR for this motor and 25 MVAR for this motor. Okay, so we found the reactive power of this motor as 25 MVAR, and for this motor also 25 MVAR. Is it fine, guys? 25, not 20. 25 MVAR. Okay, perfect. Now Current supplied by both the machines are equal. Synchronous reactance of machine A and B are, okay. Now the synchronous reactance of machine A is given. This is machine A and this is machine B. Okay, the synchronous reactance of machine A and B. This is 11 point, how much voltage was this? 11 kV. This is 11 kV. So per phase it's 11 by root 3 kV. Okay, the reactance of machine A is 1. This is J1 and the reactance of machine 2 is 3. So it is J3. Okay. Assuming the magnetic circuit to be linear, the ratio of excitation current of A to the machine B. Okay. We need to calculate the ratio of excitation current of this machine to this machine. It means if somehow we can calculate the ratio of EF to EF, EF1 to EF2, that ratio will be same as the ratio of excitation current, because that current is responsible for the flux and the flux is also responsible for EF1 and EF2. Okay. So you can calculate this ratio EF1 and EF2. If somehow you can calculate this ratio, this will be the ratio of IF1 and IF2. I hope you understood it. Okay. So this way you can calculate this current ratio, field excitation ratio. I hope you understood it. Okay. Raju, I'll come to your question. Maybe let me complete this question first and then I'll come to this question. Okay. Sir, PYU question, positive or negative along needed, sir? Okay. Gate aspirant. I'll come to you. Positive and negative, I'll come to you. Positive and negative, you can tell, na? You can tell the positive and the negative value. No problem. It's simple. You can easily calculate whether the value is positive or negative. So now IF1, IF2, this ratio is asked. How to calculate this ratio? This ratio can be calculated using EF1 and EF2. Okay, EF1 and EF2, by using this ratio you can calculate IF1 and IF2. Now what is this ratio? We know that the current is same. We know that the current value is same, and this machine is supplying this much of reactive power, and this machine is supplying this much of reactive. The reactive power is same. So both the machine have same current. Now can you calculate the current value? Yes, we can calculate the current value. We know that the reactive power for machine A is 25. So 25 is equal to 25 MVAR. So 25 per phase power is 25 into 10 to the power 6 divided by 3. This is the per phase power. That is equal to terminal voltage per phase, that is 11 by root 3 into 10 to the power 3 into IA into sine theta. IA into sine theta. Sine theta is 90 degree because only reactive power is supplied by the motor 1. So it means the power factor is 0. So sine theta is 1. So this way you can calculate IA. So IA is equal to the current supplied by the motor is equal to the per phase current. You can say it will be 25 upon 3 into 10 to the power 3 divided by 11, and in the numerator you have root 3 divided by 10 to the power 3. Is it fine, guys? So this should be 10 to the power 6. So if you cancel it, this will be 10 to the power 3 and this will be root 3. So you can say that it will be 25 upon 11 root 3 kilo ampere. Is it fine, guys? This much of current is supplied. Okay, and the angle is at 90 degree. Okay, angle is at 90 degree. Okay, so you can say that we found if this voltage is at 0 degree, the current of this machine and this machine we easily found. Since lagging reactive power is supplied by this motor, it means they are taking leading reactive power. So this current which is coming to the motor, will be at 90 degree angle because they are taking leading reactive power. This machine is also taking leading reactive power. It means if they are taking leading reactive power, it means the current should be leading. And leading reactive powers, if they are taking, it means you can also say that they are supplying lagging reactive power. Okay, is it correct, guys? So they are taking leading reactive power. It means whatever this current is 25 upon 11 root 3 into 10 to the power 3, this should be at 90 degree. It should be leading current from this voltage. It should be leading current. Is it fine? Similarly, this current should also be the same. Now, by using the KVL, you can calculate EF1 and EF2, because you can apply the KVL here. EF1 is equal to whatever this voltage is. This voltage is 11 by root 3 into 10 to the power 3 angle 0 minus this drop. This drop is J1 into this current 25 upon 11 root 3 into 10 to the power 3 at an angle of 90 degree. Is it fine, guys? Is it fine? This will be EF1. Now you can calculate it. Minus J means angle minus 90. That angle minus 90. If you add it, na? If you add it, okay, and this J can be replaced. This J can also be replaced with. So this minus J can be replaced with minus 90. This minus 90 is cancelled with plus 90. So now you can add these two quantities and you'll get EF1. So EF1 came out to be, this 10 to the power 3 is common, okay, and root 3 is also common. So 1 by root 3 into 10 to the power 3. This I have taken common out, and inside the bracket you have 11 here and 25 by 11 here. Okay. This way you can calculate EF1. Similarly, you can calculate EF2. In case of EF2, you have 3 here. Here you have 1. Here you have. Now in case of EF2 will be 10 to the power 3 by root 3 bracket 11 plus. Here should be 3 into 25 by 11. Okay. So 75 by 11. Is it fine, guys? Is it fine? This will be my EF2. So we have applied KVL. Using the KVL, we can calculate EF1 and EF2 and find the ratio. Okay. Once you get this ratio, the same ratio will be IF1 over IF2. I hope you understood it. Is it fine, guys? So this ratio came out to be, let me check this ratio. I have already calculated it. So this ratio came out to be 0.745. 0.744. Yes, Raju, that's correct. This ratio came out to be 0.7, because you have to take this by this, na? So it will be, if you can calculate, 11 plus 25 by 11 divided by 11 plus 75 by 11. Please check this ratio. Okay, this ratio came out to be 0.745. 744 or 745. This should be the correct answer. Is it fine, guys? So it's easy peasy. Again, I have converted this problem, the machine problem, into network theory problem. Okay, I have just made this diagram and then applied the KVL concept. So this way you can solve this question. I hope you understood it. Let's move to the next question, guys. In the next question, if a synchronous machine is running at leading power factor, yeah, let's come back to the previous question, gate aspirant. So gate aspirant was saying about P and Q. Okay, in this problem you are saying the sign of P and the sign of Q. So you can say that this line is lossless. So what you can assume is, you can assume that the line is reactive, Jx. You can represent its reactance as Jx. Okay. Now you can apply for active power and reactive power. Delta is 10 degree. So the active power expression is EF is 0.95, Vt is 1. 0.95 into 1 divided by x cos 10. Okay, cos 10 is positive. Is it fine? So this way you can write for active power and reactive power expression. No problem at all. So you can calculate the sign of active and reactive power. Is it fine, guys? Okay. Is it fine? So this way you can check the sign also, na? There is no problem at all. The line is lossless. It is given that lossless line per unit of 2 synchronous machine through the lossless line 0.95 angle 10 and 1 angle 0. Okay, what will be the real reactive power of machine 1? Okay, I don't know which one is machine 1. I think this is machine 1. If this is machine 1, if this is the machine 1, then this will supply the power, and the power supplied is, you can say that this is EF, this is Vt. So you can say that EF into Vt by XS sine 10 degree. Okay, if this is the machine 1, so it will come positive. If this is the machine 1, then it will take the active power. So the active power for this machine is negative. Okay, I don't know which one is machine 1. Please clarify this. I don't know which year the problem is asked in GATE, because I don't know in which year this problem is asked. Anyway, maybe if it is the PYQ, then I will take this question in some other session. Anyway, I will take this question in some other session. Let's come to the next question. So I hope you understood how to solve it now. It's very simple. It's not that much difficult. You can assume that this is Jx. Okay, and now you can comment on if let's say this is machine 1. So this is leading. So we call it EF and we call it VT. Okay, so the power flows from EF to VT. Machine 1 to machine 2 to machine 1. Let's say this is machine number 2, this is machine 1. So the active power supplied by the machine 2 is absorbed by machine 1. So it means machine 1 is absorbing the power. So the active power will be negative. Okay. Similarly, you can comment on the reactive power. Let's move to the next question. If a synchronous motor is running at leading power factor, okay, the synchronous motor, remember the synchronous motor is working at leading power factor. Leading power factor, when does the machine work on leading power factor? Obviously, if the internal excitation is more than required, it means if the machine is overexcited, you can say that. If EF is larger than VT, okay, then you can say that. Machine is working at leading power factor, its excitation induced EMF EF is equal to terminal voltage VT, higher than the terminal voltage VT. I think B is correct. Okay, because let me draw the phasor diagram. Okay, for the synchronous motor, let's say this is my VT. Okay, now it is working at leading power factor. It means IA should be on this direction. Let's say IA is in this direction, then JIXS will be in this direction. Okay, so what I can do is I can take this EF on this side now. EF plus JIXS. EF plus JIXS is VT. So if IA is leading, then EF must be greater than VT. Even if the power factor is unity, let's say that I take the power factor unity, then also EF is greater than VT. If this is IA, then EF must be this. This is EF and this is JIXS. EF plus JIXS is VT. Is it fine? So even at unity power factor, EF is greater than this length is greater than this length. So even at unity power factor, you can say that EF is greater than VT. And since the machine is working at leading power factor, so EF will surely be greater than VT. Okay. So the induced EMF EF will be greater than the terminal voltage VT. I think this is easy and you can easily solve this question. Now this is question number 10 and there is one more question, question number 11. Okay, there are some other questions also. So there are actually 12 questions, but the time is over because I have taken already 1.5 hours. Anyway, let me tell you the idea. So in this question, what is given is a 3-phase 50 Hz generator supplies a power to 3 megawatt at 17.32 kV. Okay, so I have this terminal and at this terminal 3 megawatt I am supplying and the voltage is 17.32 kilovolt. Okay, to a balanced 3-phase inductive load through an overhead line. Obviously I have connected an overhead line through which this power is supplied and the power is supplied at this volt. The per phase line resistance and the reactances for this line, the per phase line resistance is 0.25 and 3.925 ohm. Okay, these are provided to us. If the voltage at the generator terminal, the voltage at this terminal, the generator terminal, the voltage is at this terminal, the voltage is 17.87 kilovolt. Okay, that's fine. Now the power factor of the load is, okay, load power factor is asked. Load power factor is asked. So this is the question on power flow. This is the question on power flow. How to do it? Assume that this angle is 0 and this angle is delta. Now first of all, calculate the current angle. So the current angle is equal to EF angle delta minus VT angle 0 divided by Z angle theta Z. Okay, Z means this line impedance, Z angle theta Z. This side is EF, this side is VT. So EF minus VT divided by this impedance is the current. Now if you can solve it, it will be EF by Z at an angle of delta minus theta Z minus VT by Z at an angle of minus theta Z. Okay, so you will get I is equal to this. This is my current I. Once you get this I, then using this current I, you can calculate the active power, which is equal to 3 megawatt, which is already provided to us, 3 megawatt. So what is the active power due to this current? At this terminal, we have Vt angle 0. So the active power will be equal to, at the receiving end, the active power will be equal to the voltage Vt into the Vt into Ia conjugate, the real part of Vt into Ia conjugate. So Vt into the first component of the current, EF by Z, cos of theta V minus theta I. The voltage angle is 0 and current angle is 0, this. So if you take 0 minus this angle, so it will become cos theta Z minus delta, okay, minus Vt into this Vt square by Z cos of theta Z, okay. This is my active power, guys. Now we know this active power, 3 megawatt. If you want to calculate the per phase, then it will be 1 megawatt. So 1 megawatt is equal to Vt into EF. We know the magnitude. This magnitude is 17.32. This magnitude is 17.87. Divided by Z. Z is the magnitude of this impedance. Okay. So you can calculate the magnitude of Z. Cos of theta Z minus delta. Theta Z is known to us. Impedance angle is known to us. But delta is unknown. So let's take it delta itself. And here also everything is known. Theta Z is also known. So from this relation, you can calculate delta. Once you get this delta, you'll get the angle of this current. You'll get this current I. Once you get this delta, you'll get the current I, and you can check if this voltage is at 0 degree, how much angle this current is. And then you can calculate the power factor. Okay. So it's very easy, very simple. You can use the power flow expression. Okay. The active power at this load end. Active power at this load end is 1 megawatt. Per phase power is 1 megawatt. No? Because I am using this per phase voltage and per phase, everything is per phase. Okay, so this way you can calculate the power factor of the load. I hope you understood it. So please do it. Let me tell you the answer. The answer should be, let me tell you the answer. The answer should be 0.8 lag. Okay, 0.8 lag. This should be the correct answer. Now let's proceed with the next question. So again, this question is again very simple. Please do it, guys. Okay, you have to solve it. Maybe some other session, maybe in some other session, I'll tackle this problem and this problem. Okay, so both are very simple. This is even directly you can say that it's 45 degree because sine 2 delta, that reluctance torque. Okay, in silent pole synchronous machine, the developed reluctance torque attain the maximum value. In reluctance torque case, you have this term na, sine 2 delta, and sine 2 delta will be maximum if delta is 45 degree. Okay, then only you'll get this sine 2 delta term maximum. If you remember the reluctance torque expression, the reluctance torque power is Vt square by 2 into 1 by xq minus 1 by xd, na? Minus 1 by xd into sine of 2 delta. This is the reluctance power, and the torque, reluctance torque will be divided by the speed. You can say. Then you will get the reluctance torque. So this will be maximum if sine 2 delta is maximum. So sine 2 delta is 1. It means 2 delta should be 90. It means delta should be 45 degree. So it's very simple. Only question is this. I need to solve this question. So please try to solve this question. Maybe in some other session I'll try to solve this problem again. Okay. So till then you can try it yourself. Okay. And in some other session, I'll try to solve this question. So up to 2019, I have taken all the questions, guys. Okay, only one question I'm giving you the homework. So maybe in some other session, I'll tackle 2020 and 21 and 22 and this question. Okay, so I hope you enjoyed today's session, guys. So don't forget to subscribe our channel and like this session if you haven't liked it. And there is one more mobile app, so you can install that app. Go to the Google Play Store and install this app. The link of this app is also provided in the description below the video. So you can go to this link and then install this app. On this app also you will get some free classes, and you can watch these sessions and you can enjoy these sessions. Okay, guys. So thank you for showing interest in this class. See you in some other session. Tomorrow I have one more session on induction machine. So again I'm going to take some classes on induction machine, also some PYQs on induction machine. So I'll consider those. I'll take those those questions. So I hope you enjoyed. So thank you and take care. Bye.